Let's start functional analysis next with the idea of a normed space. Let X be a vector space over the field K, where K is either the field of real numbers or the field of complex numbers. A norm on X is a function which we denote by this symbol. Here in place of this dot we are going to put the input, which will be a vector from X, and it's a real valued function which satisfies some conditions. The first condition, for any vector X, its norm value is a non-negative real number. It is never negative, it's either 0 or positive. Second condition, for any vector X, the norm value is 0 if and only if the vector itself is 0. That means the 0 vector has its norm value 0 and any non-zero vector has a positive norm value. You can call this condition non-negativity and this condition non-degeneracy. Third condition, for any scalar alpha, which in general is a complex number, and any vector x, the norm value of the product alpha x equals the absolute value of alpha times the norm of x. This condition is called homogeneity. And finally, number 4, which has the name triangle inequality. This one says that for any two vectors x and y, the norm of their sum is less than or equal to the sum of their norms. Then this pair consisting of the vector space x and the norm function on it is called a normed space. Do not forget that when you are considering a normed space, basically it's a vector space, but not just a vector space, but a vector space with a norm function on it. Do not forget that the underlying field is either the field of real numbers or the field of complex numbers. It's nothing else, okay? Okay, so now we have a normed space, and now using this norm, we define this function next, D. D is a function from the Cartesian product x times x into R. D is also a real valued function, just like the norm. But unlike the norm, the domain of D is not x, it's x times x. And the definition is this. For two vectors x and y, of course, coming from x, D of x comma y is by definition the norm of the vector difference x minus y. Does this function make sense? Say you choose two vectors x and y. Then this difference is also a vector and a unique vector. And the norm of that vector is a unique real number. So yes, this function is a legitimate function. What are the properties of this function, which you can immediately derive just from this itself? Just from the definition. So we note the following properties. This is number 1. For any two vectors x and y, the d value of x comma y is this norm value, which of course is non-negative, by the first condition on the norm function itself. Next, number 2. Again we take two vectors x and y in x. Now suppose x is equal to y, then d of x comma y is of course just this. However, this x minus y is now the 0 vector, and the norm of the 0 vector is 0. This comes from condition 2 for the norm function itself. Conversely, if the d value is 0, then that means this norm value is 0, but then again by non-degeneracy of the norm function, the vector itself has to be 0. Only the 0 vector has 0 norm. Non-zero vectors have positive norms. But then from this it follows that x is equal to y. Next, number 3. Again we take x and y in x and consider d of x comma y. By definition, that is norm of x minus y. Now in the vector space x, x minus y can also be written as minus 1 times y minus x. It follows from elementary properties of vector spaces, you already know. But then by the homogeneity condition for norms, the third condition, this norm equals the absolute value of minus 1 times the norm of y minus x. This one of course is 1, so you get norm of y minus x, which is d of y comma x. So you find that the d function is symmetric. Does not matter in which order you consider the vectors, the d value is the same. And finally, we have another one, number 4. Here we consider 3 vectors, x, y and z. And say we consider d of x comma z. By definition, it's the norm of x minus z. Now you can write that as this also, introducing this intermediate minus y and plus y. So by the triangle inequality for the norm function, this will be less than or equal to the norm of x minus y. You treat this as one vector plus the norm of y minus z. You treat this as another vector. This, however, is d of x comma y and this one is d of y comma z. So you see that d of x comma z is less than or equal to d of x comma y plus d of y comma z. So these 4 properties are familiar to you. What do they tell you about the function d? That d is a metric on x. It's called the metric induced by the norm function. So that means you now have a metric space. You started with a vector space x on which you have a function called norm. Using that norm, you defined a metric d on x. Now, if this metric space x comma d is complete, recall that completeness means that if you consider any Cauchy sequence of points in x, which will be vectors because we are in a vector space, then that Cauchy sequence converges to a vector in x. If that happens for all Cauchy sequences, then we say that this metric space is complete. If this one is complete, then we call the corresponding norm space from where this is actually coming a Banach space, named after the mathematician Stephen Banach. Now I am going to end this video with this simple observation. It's the property, you can say it's an elementary property of the norm function itself, that it's a continuous function. Continuous in what sense? We understand that this space has a metric, but x also has a metric. With respect to these two metric structures, we are claiming that the norm function is a continuous function. Now, in order to prove this fact, this continuity, we need an inequality, which is true in any normed space. So let's first establish that inequality. It's not triangle inequality, but another similar inequality which follows from the triangle inequality. So x is our space, let a and b be 2 vectors. Now we start with the norm of a. In place of the vector a, we can of course write a minus b plus b, and then you use the triangle inequality for the norm function. That gives you this. This norm is less than or equal to the norm of a minus b plus the norm of b. So if you then subtract norm of b from both sides, you get this. Norm a minus norm b is less than or equal to norm of a minus b. Now we interchange the vectors a and b, which of course we can because in this calculation a and b are arbitrary vectors. So if you write b in place of a and a in place of b, the same thing happens. Same thing means you have to write the correct thing. If you write b here and a here, here also you have to do that same thing. So you get this. Norm b minus norm a is less than or equal to norm b minus a. But in a previous calculation, we saw that this is nothing but norm of a minus b. So what do you see here? You see that norm a minus norm b is less than or equal to norm of a minus b, and its negative is also less than or equal to norm a minus b. And what does this tell you? It tells you this, that the absolute value of this difference is also less than or equal to norm a minus b, because both the number and its negative are less than or equal to this. So the absolute value of the number will also be less than or equal to this. And this is the inequality that will give us the proof of this fact. Okay, so now we prove Let x be any vector in X, we will prove that the norm function is continuous at this point. And accordingly we choose an arbitrary positive real number epsilon. Now we need a delta, for which you know what happens. We choose delta equal to epsilon itself. Now for any vector y in X such that the norm of y minus x, or we can say the distance between y and x, because it's that d of y comma x, and now you know that d is a metric. So for any vector y whose distance from x is less than delta, we have this. You note these two inequalities. This is what we have used here. The numerical difference between norm of y and norm of x is less than or equal to norm of y minus x, which is less than delta, but delta is epsilon. So that is why the norm function is continuous at x. And finally you note one more thing. Oh, and before I say something else, what is x? X is any point in the vector space x, any vector. So that is why norm is continuous throughout X. It is in general continuous. Now what was I going to say? Note carefully that the choice of this delta depends only on epsilon and not on the point X. I mean, had you chosen some other vector, for that vector also, we can choose this delta for this given epsilon. So the choice of delta, which in general depends both on epsilon and the point at which you want continuity, in this case is independent of the point. So that is why this continuity is uniform continuity. So this function is not just continuous, but it is uniformly continuous throughout X. So let me end the video with this. In the next video on functional analysis, we are going to see examples of normed spaces.